Anyway, one of the things that the Scholl Chair in international business does is look at global value chains and study them, and in particular looking at new technologies that is going to affect the development of those supply chains and thereby affect the trading system and the way it works. One such technology is additive manufacturing, which is the politically correct term for what used to be 3D printing. So we will refer to it as AM, just like we also have AI, artificial intelligence. There's acronyms for everything. We've been able to do a study on this, which I think is noteworthy because it really is a work for laymen and not for technicians. One of our goals here at the chair is to try to put into regular language for non-experts what these technologies are, how they work, and what they mean. What they mean for manufacturing, what they mean for the job base, what they mean for the trading system. And so I'm particularly happy to be able to roll this one out. And to do it is my predecessor in the Scholl Chair, Scott Miller, who is, as far as I'm concerned, one of the town's leading experts on supply chains and has written about that subject often, and was really the instigator of this particular study, which is funded by a generous support from the Arconic Foundation. Scott may have a bit more to say about that. And so Scott's going to present the paper. We've got a few slides, and then he and I will have a conversation briefly, and then we'll open it up to any questions that all of you have got. So. Okay. Scott, go for it. And if your microphone doesn't work, you can have this one.
We're going to find out in 5 seconds. I think I'm fine. All right. Thank you. And thanks, Bill. I appreciate the kind introduction, and let me add my welcome. This is a bit of an un-Washington kind of product, but that's intentional. We were delighted to be able to dig in at some depth to this rapidly growing technology called additive manufacturing and look at it from all angles. But we realized the audience that was not being served were policymakers. There's probably a conference a month for technical experts or engineers on this topic, but almost nothing for the person who's non-technical orientation but is confronted with policy choices. Thanks to CRS, we identified the fact that of the 535 members of the House and Senate, there are 8 engineers by training. There's actually a PhD physicist, oddly enough, Bill Foster of Illinois, and there's a PhD mathematician in the Congress. But other than that, it tapers off pretty quickly in terms of a number of physicians and medical professionals, but not a lot of people with technical backgrounds. And so a lot of the material that was being presented simply was not digestible in a straightforward manner. So our task from the foundation, once we shared this fact set with them, was to produce something that was easily readable by someone without technical expertise and could be digested, say, by a member of Congress on the flight home to his or her district on the weekend. So it's I think 15 pages long, which was the outside limit, interestingly enough. Again, an un-Washington objective, but I think one that we hope will find this paper a pretty broad audience. That's what we started with as a goal. And so we started with trying to talk about what is additive. For those of you who aren't familiar with it, we will start there. Let me see if I can advance there it is. Okay. National Institutes of Science and Technology has helped identify a definition for additive manufacture. It's simply the process of joining materials layer by layer. And basically, if you think of machining or forming a material, there are 2 things you can do with it. You can subtract material, which by milling or machining or grinding, or if you're Michelangelo, by chopping away at the block of marble till you get to David. But so that's classic subtractive manufacturing. And additive manufacturing is simply the reverse, where through the process of lithography or laser sintering or 5 other identified processes, which the report goes into, you add layer by layer to form the materials into an object or device. Now, additive manufacturing got its start in the late 1980s, early 1990s, and what we've learned so far is there are a couple of areas of manufacturing and production where it has amazing advantages versus the alternative, versus machining or assembly. One of them is in complex geometries, and this would be a part that has internal channels or internal cavities, and it's sort of think of a structure within a structure. These are not particularly efficiently machined, but can be built up through the additive manufacturing process. So this notion of a part with complicated geometries is one of the places where 3D printing is expanding rapidly. Also, highly customized parts. Think of this as replacement parts that are no longer in production. In fact, I became familiar with additive manufacturing because I'm a YouTube watcher by subscription of Jay Leno's Garage. And Jay Leno had a 1915 Winton, which is a lovely car, but the Winton Automobile Company's been out of business for not quite 100 years, but close to it. And so finding a new valve cover for his 1915 Winton was quite a challenge. The parts have been out of stock for 50 years. But he would manage to use a laser scanner and have a company 3D print an identical but functioning valve cover for his 1915 Winton. Now that's a classic example and seems odd, but if you think of the business of spare parts and maintenance of machinery and equipment, particularly in the Department of Defense, where there's a lot of legacy equipment, this becomes a wonderful application of a technology that's uniquely suited for it. Likewise, customization is very important in certain other areas of manufacturing. Think of medical devices. So one of the categories that rapidly converted to additive manufacturing happened to be hearing aids, because while hearing aids have a similar design and a similar shape, the precise structure and shape and dimensions of your ear canal are quite different than the next person. And by taking precise measurements, you can 3D print a hearing aid that's ideal for you and functions best for you because it's such a precise fit. So this idea of being able to customize parts with additive manufacturing, both for the maintenance and spare parts side, and also sort of precision, personal tailoring of the device, have great advantages. Now, 3D printing won't take over manufacturing. Additive is not for everything. There are some things where normal sort of subtractive manufacturing, machining, drilling, fitting, will retain its advantage. One of them is scale. 3D printing and additive manufacturing has not yet produced parts, multiple parts at scale. A second disadvantage for 3D printing is the size of the part. A very large part would require a very large chamber of these printing devices, and often it's less expensive and faster to machine large pieces than it is to print them up layer by layer. There are also some very simple parts, simple machine screws, simple components, flat stampings that will probably always be part of subtractive manufacturing or conventional production techniques. However, additive manufacturing is expanding the boundaries in a lot of ways in the materials it uses and in the applications that it finds and the places you can actually operate these 3D printers. The paper then goes through a series of sort of milestones of how this technology came about. It seems disruptive and breathtaking at the moment. It actually grew from a very small base, but grew quite consistently and quite rapidly. As I said, 1980s was the first laser sintering, usually with polyethylene, where layers were fused together with a laser. In the early 2000s, though, the most important sort of branch in the technology paths occurred, and that is basically part of the industry focused continually on prototyping, and a lot of the application for additive manufacturing is to simply and quickly create a prototype and then you can scale up with mass production. And the prototyping business is very important to a lot of developers and a lot of manufacturing firms. Prototyping took its own route and worked toward speed and cost reduction, to the point that I mentioned to Bill before we started. Today I went to Amazon.com and entered the search term 3D printer, and I found out for $199 I can have a 3D printer for prototyping delivered to my office and operate it from my local network.
Delivered by drone, I presume.
Well, conventionally or by drone, either way, one. But for $200, I can have my own 3D printer. Now that's for a prototype. The other route, and what's actually becoming more significant in terms of the volume and structure of the industry, is 3D printing for finished components. And these tend to be not out of polyethylene, but out of the material that is needed for the specification or the condition. They're highly engineered finished components with a high degree of sophistication, both as perhaps replacement parts, but also in the next generation. What currently is happening is parts are being engineered for the parameters of 3D printing. So instead of replicating a part that was made with conventional manufacturing techniques simply because it's not available, the new parts can be developed in a way that uses the advantages of 3D printing. One of the better examples in the literature is one from GE Aviation. GE Aviation uses, if you run jet engines, you use fuel nozzles. And their new generation fuel nozzle, manufactured conventionally, has 18 parts in the nozzle itself. The additive manufacturing version of that part that functions identically is built up as a single component. 18, one part. So that's the level of engineering that's in the new component, but also it is the way that technologists and engineers are learning of materials and beginning to apply them in ways that really leverage the nature and unique opportunities of the technology itself. The ASTM has been very important as a private standard setting body, and in 2009 they established a committee and began to sort of categorize and lay out the geography of standards that might be required for the development and implementation of additive manufactured parts throughout the system. The last line is what I find important, since the Wohlers, which is an industry advisory group, notes that from 1998 to 2016, so during that period, the compound average growth rate was 25% for additive manufacturing. So that's, the rule of 78 would say that's a business that doubles every 3 years. And so it's happening, it's coming very fast, and while not quite Moore's Law level exponential technology, it is growing very fast and becoming a part of a lot of what we see and what we experience around us. The paper also looked at sort of the key challenges, and there are three general areas. I'll leave you to read the paper. You'll probably have time to read it in the taxi on the way back to the office. But the one area is course technology. There are in this space an interesting set of suppliers in that there are a lot of small businesses active. This is true in the United States, in Israel, in Germany, every place we looked at it. There are many small entrepreneurs involved in the production of components using additive. Now that is going to probably consolidate at some point. It hasn't yet, but as larger manufacturers look for a secure and stable supply base, I think you'll probably see consolidation. That tends to happen in a lot of industries, so it wouldn't surprise me if it happened here. But the technology is advancing very rapidly, and in many cases, the regulatory agencies are supporting this with quite disciplined and open-minded approaches. The input control and monitoring of these processes to get to finished parts is very delicate and has to be managed very, very carefully to get a finished product the quality you want. So the aviation parts is a good example. Aviation obviously tightly regulated. The FAA is deeply involved in parts and components for aircraft, and at the moment they've identified 100 process parameters in the production of a 3D printed part that need to be monitored. So whether it's the material, temperatures, input, ambient humidity, all kinds of conditions of the materials themselves. Because as you print the part, you have to be careful in a lot of respects not to create voids inside. Materials have to flow as predicted. There's a whole lot of parameters control. So it takes a high degree of sophistication. The people who are involved in this are basically, imagine a machine the size of this stage that's basically a little foundry that's creating a part out of titanium or aluminum or magnesium, whatever the substance might be, and doing it at layer by layer at a very precisely controlled level. So this technology is well suited to the current regulation, but it's one of the things I think regulators are going to struggle to keep up, in my view, with the technology as new materials get introduced, as new conditions get introduced. In terms of workforce development, this is one. It has the same general characteristic as a lot of advanced manufacturing, which is there actually is a lot more demand than supply for qualified advanced manufacturing technicians in the United States. The Manufacturing Institute, which is the research arm of the National Association of Manufacturers, estimated that there's about 3.5 million jobs in advanced manufacturing in the United States, and about 2 million of those are noted as difficult to fill because of the lack of qualified candidates. So there's an opportunity. The opportunity of training and development also extends to the technicians and regulators involved in the design of these products, because many of the engineers who are responsible for additive manufacturing projects started their career in conventional manufacturing, are adapting and learning the skills. They're developing it very fast. They're smart people who are committed to it, as are the regulators. But this thing is evolving rapidly enough that I think that's an area that policymakers ought to give thought and focus toward. Finally, security and intellectual property. Like most advanced manufacturing processes, it's all basically code. The part is designed in the computer. The instructions for the machine are computer controlled, and that gives you two sets of risks to manage. One is the sort of the security of the transmission itself. So you need to avoid the kind of interference which would alter the instructions between the machine and the part and lead to defective parts. You'd also have the intellectual property to protect. It's harder than you might imagine. There was a very interesting case at the International Trade Commission on the Section 337 case, which had to do with a 3D printed series of parts, which were the invisible orthodonture. Invisalign is the brand name
braces
that we know of. There was apparently a firm in Turkey, if I recall correctly, who was providing the instructions, the code, for a dentist's office in Texas, and the code was pirated. Or there was at least a claim by an American firm that their intellectual property had been stolen by the firm outside the United States. And because the Section 337 was written in the 1920s, and the definition of what an article in commerce did not include computer code transferred over data lines, the U.S. Complainant was unable to get an order against the importation of the pirated code. So there are intellectual property concerns. Obviously, like all advanced manufacturing, it's really all about the IP. And with that, both IP and protecting, making sure that parts that are designed in a certain way to perform in a certain way actually get produced the way they're designed, and there's no sort of interference with the production of the component itself. So those are challenges that with all advanced manufacturing, I think they're particularly critical with additive, because additive is so far quiet. It surprises people that it exists. You'd be surprised if you flew on a jet that one of the nozzles for the engines was actually produced with additive. That would surprise people. So far, performance has been excellent. It's the equivalent of performance of a conventional part, but a catastrophic failure would probably do harm to the industry at a pretty critical stage. So I think those are the things that as we review the industry, the elevator ride with the policymaker is focus on getting the regulation right, getting advances to regulation, and some open-mindedness along with the need for performance of the finished part. Get workforce development issues straight so people can actually do this skill and develop the technology and watch the IP. So that's where we wound up in the report. We tried to make it easy to deal with, and I hope you enjoy it. I hope the report has the effect we intend, and I look forward to your questions. Thank you.
Thank you, Scott. Let me start with a couple questions, and we'll turn it over to the audience. One that occurred to me while you were talking, so I'm going to deviate from the
Sure,
script.
no problem.
The report and most of your conversation has been about the printer, about the machines and what they make. Who makes the machines? Are there a lot of people who make printers? And what do we know about that industry?
There are a number of producers. They are essentially descended from the machine tool industry. Many of the expert producers of machines are German companies at this point, some of the best technology, which is probably consistent with high performance machine tools as well. But they tend to be quite sophisticated machines. There have been US acquisitions of small, especially German, but also American companies in the printing business. The machines are thus, to this point, specialized in the same way the technology split. So there's a broader range of producers for the prototyping machines, a narrower range of the producers of the much more expensive, more sophisticated machines that are intended for finished product.
Do you think there's going to be consolidation upstream as well as downstream?
I would expect it, yeah. It almost always happens in new and expanding, particularly mechanically oriented industries. Happens to a lesser extent in chemistry, because chemistry is almost always working with scale. But the number of small producers are likely to consolidate, and the way it's happening now is through acquisition.
And the other major producers, other countries that are big in this, you said, are Israel, Germany?
Yes, Israel and Germany would be two leaders. Japan has a number of projects going, but Germany would be outside, at least about half the production of both the machines and the 3D printed parts, if I recall correctly, are in the United States. But the other half, Germany would be the leader.
Is this something the Chinese have picked up on as well, or not?
Not to the extent. They are in the prototyping business, and so there are Chinese-made prototype machines, but I've not seen in the literature much on the machines that produce the highly engineered finished products from China.
One of the things you mentioned was about regulation, which is inevitable in something like this, and you illustrated that on the aircraft side with the sensitivity of the product and the consequences of catastrophic failure. Can you talk a little bit about what federal agencies are involved in regulation of AM, and are any of them better at it than others?
Sure, yeah. I think the agency that I would point to as being fastest to integrate this into their operations was the Department of Defense. And it happened through the applications in what the DoD people call sustainment. And this is sort of the spare parts and supply part of the mission of the Department of Defense. So there is both the DoD's acquisitions projects themselves and the National Defense Industrial Association, which is the private association that works with DoD, that have focused on finding the applications for this, and the applications have driven the regulatory envelope. The other two areas which there's lots of literature on very constructive engagement from regulators is the FAA, who have a very difficult, sophisticated products, but they're taking it on. They see the benefits of the technology. And the FDA, interestingly. The FDA in the device business sees enough future in the technology, and particularly as new materials become involved, that there's a surprising sort of acceptance and embrace of the technology at FDA, which is helping in the medical device business.
Did you look at all into the human organ printing?
I did not, although there is good technical work being done on lots of using biologics and biologic material as the substance which goes through the printer. So it also gets you into a very interesting customizable pharmaceutical model.
This is, to me, one of the most fascinating potential applications. If you need a new kidney, maybe this is something, not now, but in the future, that we're going to be able to print, and as he described, we'll be able to print to your body specifications. So probably in that, and if you use material that came from your body to begin with,
Yeah.
then you don't have the same kind of rejection issues.
That's
I think.
likely
Yeah.
a benefit. Probably what will come first is what you and I have benefited from already, which is metal hips or metal knees
Yes.
that are also designed for your particular size, shape, and geometry. So,
I think actually that reminds my doctor told me about this I got a new hip last summer, so it's on my mind. But in my case, it wasn't a general anesthesia. You were sort of fading in and out. At one point, I heard this sort of bang, 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 this hammering, which was a little disturbing. And I asked him about it afterwards. He didn't want to talk about it, but eventually said, "Well, just think of me as a carpenter, and we have to make everything fit." This was not reassuring, but
orthopedic surgeons have a lot in common with car mechanics.
well, the reality is these things come in standard sizes, and
Right,
you have to, sometimes you have to force them a little bit if you want
Right.
them to fit. But you're exactly right. And what he said was, give it a couple years,
Yeah.
and these things will all be done with AM, and they won't be handled the same way. Although they still will probably be made out of the same materials.
Yes, likely.
Now, you led into another question that I wanted to ask you, which is the role of the private sector in regulation and standards development. The private sector are not regulators, but
Right.
in the United States at least, the private sector has often played a very significant role in the development of standards and has interacted with regulators in helping them devise the standards they're going to measure products against. Is that happening here as well, or not?
Yes, and ASTM actually was probably the earliest private organization who was involved in developing standards for additive as the technology grew. They got in early, did a very impressive job. There was also a partnership formed, what was called a national accelerator. It's of all places in Youngstown, Ohio, and called America Makes, which was a nonprofit setup. It was public-private partnership, but it was intended to accelerate. And what America Makes has done since 2012 is provided a lot of convening power. They brought together the equipment manufacturers, the people who make the materials that are used in 3D printing, the people who are customers for the parts, and the regulators and the standards entities together, and looked for ways to sort of solve problems. So a lot of the work has been done through a consortium, which I think has advanced the technology.
Are there international implications of this too? I mean, is ISO or the Europeans doing the same thing? Or
Yes, ISO has an extensive project in this, as do the Europeans. But ASTM works with ISO and has worked explicitly with them throughout this. But it's likely to be an area, much like almost any other area of standard setting, where the degree of international harmonization has its limits.
Well, that's what I was going to ask you. Do you see this moving in a compatible direction, or do you see it becoming a trade issue with incompatible standards and therefore a trade barrier?
I would expect it to become a trade barrier, particularly as the applications get more sophisticated and countries or national champion firms find advantages.
One would think, I mean, that's not unusual,
Yeah.
and there's numerous cases of that going on now. They tend to be, I think, most prevalent in sort of old manufacturing, because you have standards that were developed a long time ago when nobody was thinking about the
Right.
trade implications, and they've just sort of accreted or built up since then. I had kind of thought that when you have new technologies coming online in a globalized world with global value chains, there would be more of an effort, certainly by the private sector, to try to put together harmonized standards so this problem didn't occur.
That's certainly in the interest of most of the private sector entities that I've spoken to.
But government gets in the way?
Well, it's unclear at this point. I wouldn't do a lot of critique. There is a good project operating between ASTM and ISO, which should at least let us know where the roadblocks might be in the future.
Okay. Well, when I read the study, I appreciated the caution, if you will, with which you approached the potential of the issue. And it's been, it has experienced rapid growth, but as you pointed out, from a small base. Talk a little bit, if you would, about where you see this coming, where you see this going. Is this going to be the next big thing and everything's going to be printed? What are some of the potentials? Where are we most likely are we likely to see any sort of explosions of use of this, and if so, where and what sectors?
Well, it's a great question. Look, it's about a $100 billion global segment now. Now that sounds like a big number, and in some cases it is. It's an impressive figure, but that's about the amount of product produced by the original equipment suppliers of the three biggest German automakers. So it's a small subset of total manufacturing output. But from that 100 billion, there are three dimensions that I think are going to be very interesting to watch, and what I'll be following as we put this project to rest and move on to the next project. The first one is the range of materials being printed. Is the more things that you can use as the substrate, the more interesting applications there are. So that's the first thing. Second, printers are getting faster, and the speed of printing is one of the key barriers to broad application of additive. Slow printers may mean the parts themselves always wind up being expensive and often lose out to machine parts. So as printers get faster, as the sintering operation speeds up, the machines find their way into more application. So that's the second. And third, particularly from the standpoint of replacement parts, or as the DoD would call it, sustainment, the conditions under which the machines can operate, they're getting more and more able to operate in sort of normal ambient conditions. You don't need a sealed room and climate control and a very carefully maintained atmosphere in the machine as you did. I noted the last season, the Formula One team, McLaren, which is champion Formula One team. Of course, Formula One travels the globe. If you follow Top Line Auto Racing, they decided to travel with a 3D printer instead of some of their spare parts. And so as they moved from nation to nation and needed a replacement part, they found it easier to print it out. So operating, the more tolerant the machine is of operating conditions, the more conditions you can see that sort of thing applying.
Well, just pick up on that for a minute. Does this mean that long-term this is going to revolutionize basically the maintenance business? That instead of having to manufacture and ship spare parts to places that run out, you just include a printer with the product to begin with, and they can print their own parts as needed?
It's entirely possible that some of that will happen, particularly with expensive components or hard to maintain components, hard to keep in supply. So it's the rare part but it is critical to operate the helicopter or to operate the machine that is likely to find an application where additive is the better solution than either normal machining and carrying an inventory or the typical form of handling spares. It won't replace machine screws, but it will. The more exotic and sophisticated the part, the more potential there is for this.
Well, I would think the farther away your location or the more remote
Yes.
your location is, it's easier simply to ship the capability than it is to constantly be shipping parts. If
Right,
it's going to
that's
take
right.
multiple days.
Especially
to
if
get
the
there.
machine can operate in sort of normal conditions, if it doesn't need special treatment.
So finally, and then we'll go to the audience, just to give an anecdote about the potential here. Can you retell the story you were telling before we began about the house?
Yes, this was actually a news item from today, so I encourage you to look it up. There's a firm that is trying to solve the world's shortage of housing, and they're in Austin, Texas. They printed a house. There's a 3D printed house. It's 800 square feet. It meets all known building codes. It's a functional, habitable house. Looks fine to me. Okay. They printed it for $4,000 in 24 hours. Total construction cost $4,000. Total time of construction for 24 hours from a concrete slab. It's impressive. Their next stop is they're taking some of these printers to El Salvador, and they're going to go build a neighborhood someplace. So this is the kind of now what that says to me is, first, they've found a machine that has a big enough wingspan and a broad enough set of operating conditions that it can function in, that it can work outside in a big space. You're not making a little prototype, you're making a house. Second, they found materials that meet all fire codes and building codes that also are a substrate that can be printed, so that's an advance. and they have been able to accommodate the design requirements of the 3D printing system into the building code requirements for the finished product. So very interesting application that, you know.
How complicated, that raises one more question, if I delay the audience for a second. How complicated is substrate creation? I mean, you've got to identify your materials, but then it's basically a powder, isn't it?
There's a tremendous amount of engineering and research that goes into those components. In fact, our sponsor's parent company, Arconic, is actually in the aluminum powder business. And I had a chance to meet with people in their R&D lab, and the level of sophistication in these powders is astonishing because they have to have flow properties, they have to enter the machine consistently, they have to behave consistently in the machine, the cooling times as the laser process ends, they have to contract at the right rates.
And they have to be uniform.
Oh, it has to be very uniform and very and very tolerant of certain variations, so you don't get a lot of parts that have to be thrown away because they have voids in them or something like that. There's probably as much engineering on the material side that enters the chamber as there is in the chamber itself and the machine that makes it.
Well, let's turn to the audience. Who's got a question? Right here in the front row. Yeah, hang on. And if you can identify yourself, that would be good, so all of our remote listeners will know what's going on.
Good afternoon. I'm TJ May. I'm an Air Force fellow.
Yeah.
Some of the engineers that I spoke with kind of talked to the fact that they see some really creative applications for AM from children because they're not limited by a traditional engineering background. Do you think that similarly regulation or applications are unduly inhibited in a similar manner? And do you think, kind of as a pile-on to that potential uses for this technology are limited by kind of the current state of technology rather than looking past or assuming some of those challenges today will be overcome?
That's a great question, and one of the reasons I suggested that one part of the workforce development challenge was for regulators themselves is this does require some unusual thinking. You've got to think about it differently. Obviously, the conditions and the safety and performance requirements of the finished part are vitally important. But how you get there, what additive manufacturing does is kind of explodes the number of routes to get to that final endpoint. And regulators and the people in those assignments who can think that way are likely to see ways around and interact with the designers and engineers in ways that get more productive conclusions. From conversations I had, I never saw anything published on this, but my sense is this is happening at FAA, and one of the reasons there's a lot of progress in the aviation space. And frankly, I was surprised by that, because aviation regulation is so conservative that for lots of good safety reasons. I mean, it's not calling it conservative is not a criticism in any way, but it was the place I least expected to see the technology, new technology being adopted so fast, and it appears to be the approach that the regulators are taking, that they understand their obligations to safety and performance under a lot of different and very difficult conditions, but they also see the potential that this produces. So I think you're right, and I didn't know about that with children, but it doesn't surprise me from what I've learned so far. Thank you.
Way in the back over there, and then we'll come back over to this side.
Thank you, gentlemen. Rob Tobias, and formerly with U.S. Treasury, now a consultant.
Mm-hmm.
Mr. Miller, you've mentioned several times about the range of materials being expanded, being used. So far, it seems like it's solid or semi-solid materials. Do you see liquids ultimately? Do you foresee liquids being used where you could replicate a liquid substance?
Well, let's see. Depends what temperature. If you're printing polyethylene, it becomes a liquid pretty quickly when you heat it. So you're modifying it, obviously becomes a solid when you're done. So I haven't seen those applications where it both starts and ends as a liquid. But given the range of options in biologics, that may be one place you see it. The biologics tend to take, organic materials tend to take sort of semi-solid forms at ambient temperature. And so that may be a condition that would where what you're asking would occur. I haven't seen it yet.
Maybe not in the context of all the social good products, pharmaceuticals you mentioned, but I was wondering if could you ultimately take an inexpensive blended scotch and have the machine replicate a 50-year-old single malt and the characteristics and features?
I would love to be part of the experimentation on that, just to get the samples.
All right, there was one over here, I thought, right here in the middle row. Thanks.
Thank you. Kyle Innes, Georgetown University. Thank you for this.
Sure.
I feel this is very, very timely. One of the things that when I look at additive manufacturing that really seems to be a potential game changer is the ability to remake the supply chain. There are a lot of knock-on effects, as you've hinted on throughout the
Yes.
conversation. Did you have a chance to look at those at all within the scope of your paper? And regardless, do you have any thoughts in terms of monitoring those as you look at policy implications for additive manufacturing?
You know, it's a great question, and I think most of the interesting dynamic in terms of changing the supply chain entirely come from basically what your starting point is. So, are you able to start with a machine instead of a warehouse full of parts, but also at the place where parts become uniquely designed for the additive technology. Think of the GE nozzle that it used to have 18 parts and now has one. Okay, that's a dramatic upgrade in performance, and so it's a lighter component. It is a more reliable component because it has fewer pieces internally. The failure rates are far lower. So those kinds of things are the things that change the dynamic, and I think will cause additive components to very quickly find application. So I mentioned hearing aids. Hearing aids was probably the fastest replacement of ordinary products that anybody's noted. Now, it's still a tiny piece of the medical device business, but the custom fit made such a huge difference in performance that basically, if you wanted to buy a set of custom hearing aids today, they would be additive only. They have basically, the supply chain has been completely changed over. So I expect that to happen, once again, as there's more experimentation, more materials, and more people thinking about how to get the same performance and safety and effectiveness out of a part, but put it together using what additive is good at instead of what conventional mechanisms are good at, and replicating that. That's a lot of thinking that will create the breakthroughs.
Right here in the front row.
Hey, Scott, Andrew Hunter, CSIS. One of the most impressive things I've seen that strikes me as an implementation of additive manufacturing, but I'm interested in your thoughts, relates to production of composite parts, which there's a lot of everywhere, but a lot of at DoD, where I spend most of my time. And this was an application where a composite part was being built, and there was a machine that was essentially, I call it robotic weaving.
Yes.
Essentially weaving together the fiber parts of a composite, and later, of course, they can insert other things in it to make it the fully finished composite product. And what was interesting about that is it almost looked like a multi-axis machine tool in terms of the way that it did it. So it wasn't just a, layer by layer growth. It was almost like it was growing inside out. And it seems like you could also potentially address some of these wingspan issues, right? If you have a machine like that, you could produce an almost endlessly long part over time without having to have an endlessly long machine. So I was just interested if you saw some of that or how you think it relates in the bigger picture.
Yes. Composite is an interesting sort of, it's partially additive in the coatings, in the way the coatings are applied. For me, the critical element for most applications would be the ability for both the machine and the material to operate in largely ambient conditions. So you can have, basically that's what happened, that's why you can print a house. You print a house because you have a machine with a long arm, that you put in the center of the concrete slab, and the machine operates in ambient air and temperature and other conditions, humidity conditions, fine. And so a lot of current additive components are produced in small chambers with careful control of all the parameters. And so to the extent that there's development in materials and the machinery that allows operation in ambient space, your dimensional problem kind of solves itself, and you're able to do those kinds of things. So we'll see where it goes. I haven't seen it yet, at least in not that people are calling one of the 7 additive manufacturing practices, but it wouldn't surprise me.
Right here.
Hi, Kasha Witkowski with HP. Quick question on the workforce piece.
Yeah.
You touched a little on, right, that there's more demand than supply. And just wondering if you've seen out there, are any educational institutions doing anything right to sort of catch up and help make sure that that workforce is there? Or, you know, maybe is DoD doing something right in training the people, since they're sort of an early adopter as an agency? Just seeing, you know, how
Yes.
we can address that.
It's a good question. The DoD programs are probably the best within the government of being able to qualify some of the armed forces talent to perform the tasks. So they're doing that well. They do that well in a lot of things. So that's part of what the Defense Department does well, is develop people. It's less even outside in the private sector and in public-private programs. Like most programs of this nature, retraining and workforce development programs, there are often some very good examples that, for whatever set of reason, are hard to replicate. So there are good instances of this. One of the best is actually in South Carolina, where because of the absence of skilled advanced manufacturing technicians, BMW, which produces trucks in South Carolina, essentially lifted straight out the apprentice program from German, what we would call technical schools or associate degree granting institutions, lifted it wholesale, deposited it into community colleges in and around their Spartanburg plant, and created a German-style apprentice program, which is working fine and creating a lot of good jobs and career opportunities for people in that area. As I said, there was a company with a specific need at a specific location that did it, okay? And now that it's known, we're having a difficult time replicating it. So, but I think the demand will be consistent enough. This is at least what the people at the Manufacturing Institute who study this told me, is that there will be a lot of demand for high-skill manufacturing tasks, and they're not punch press operator jobs. They are process control technician jobs, and the process control technician has a set of very sophisticated tasks to do. It's a highly technical work, but it is really well rewarded in compensation. So they think that, you know, like most things, demand will create the supply, but we're behind the curve at the moment.
John first, and then we'll get to you next.
Hi, thanks for the great report. John Pacheco with Pacheco Global Partners. I was just recently at USTR negotiating standards and battling the EU over and over again on many of these issues. So I appreciated the discussion of that in the paper. I thought it was very good, particularly with regard to the EU's practices in third countries.
Yes.
In terms of negotiating those into their agreements and preventing access for US products. I had a question about the industry itself, and I think you rightly recognize that these standards can become barriers to the entry of U.S. products. What is the U.S. industry, and is it an export industry yet? Is it the materials? Is it the code behind the the design of these things that come out of the printers, or is it the printers themselves? And what are we sort of advocating for in terms of access?
The U.S. industry is quite diverse, and it's somewhat hard to characterize because of the number of small firms involved. And so what struck me about it as I got into it, you can see this if you go to America Makes website and just Google it. It's easy to find, and look at their member list. There's some household names there. There's some kind of brand name companies that you've heard of and you could expect in this space, like GE and Boeing. And but there are members you had never heard of. You probably couldn't tell them from a local law firm, and they're probably producing a material or a device or a substrate or something. So at the moment, the industry is very fragmented. It tends to have a lot of small players involved, and because of that, their customers are coming from wherever they come from. They probably don't have an explicit international strategy yet. Now there is consolidation, and General Electric, which GE Aviation is strategically committed to additive manufacturing, and are making a series of strategic acquisitions of mostly small machine makers, the people who make the sintering equipment to the little foundries, essentially. And so I'm seeing the trend of industry consolidation is one that I think is logical and natural and will happen relatively quickly. As you get larger firms involved, the firms themselves will begin thinking geographically, thinking about future customers in a way that it's not now. It's kind of refreshing now when you go to I went to a convention in Pittsburgh where there's a whole convention center full of these machines and people involved in the business, and they were all just inventing, and they were just happy to be advancing technology. They were finding new ways to make things, and not a lot of people thinking about the grand strategy. So I think it will evolve, though. Yeah. Yes.
Over here next.
Well, thanks. I'd like to add my compliments to what a great discussion we've had so far. I'm Jeff Grove with ASTM International.
Great.
So we've been working on some of the
Thank you.
standards work that
You've
you
been
mentioned in the
terrific.
report.
Yeah, right.
So thank you for that. And I would just like to share a couple comments that lead
Sure.
to a question real quickly. I think you're absolutely right that the threats from a global regulatory standpoint could be a real threat to this exciting new area of technology and the enabling factors that this technology has. So the approach that we've taken is really twofold.
Mm-hmm.
One is that these companies, because of the significant investments they're making throughout their value chains in AM, they certainly don't want to spend millions of dollars creating a process that has to be duplicated to match different regulatory structures. So we recognize there's a duplication of effort issue.
Right.
And second, we recognize that there's an acceptance issue. Sometimes the standards that are developed, whether it's by ASTM, Society of Automotive Engineers, ASME, certain U.S. domiciled organizations, all that meet the World Trade Organization's principles for international standards.
Right.
There's still some legitimate technical barriers to their acceptance in Europe and elsewhere.
Yes.
So we've entered into these agreements, and I think you mentioned that. One agreement is with the European standards body, CEN, and the ISO, the Geneva-based international standards body. And really what's great about these agreements is that it provides an ability then for the European Commission and for the national standards bodies of Europe to nationally adopt these very same standards that are being developed, and they can become the European norms. So we've already got 6 examples of standards that have been developed with heavy participation from North American and European companies. But now we've seen those standards, the very same standards that FAA, NASA, and DOE and other leading U.S. agencies are using. We're seeing them adopted as the national standards and the European norms in Europe. And we're hoping that that's a strategy that will continue to address some of the efficiency challenges that can be created by the global regulatory environment, which you mentioned. And I'm just wondering if there's any other pathways that you can think of to help eliminate some of the potential regulatory barriers and trade barriers that could happen for this exciting area.
No, first, thanks for coming. Second, you're doing great work. STM has been in the forefront of standards and technology advancement for this sector, as far as I can tell from all the research. So well done. The fact that you've got Europe covered in your plan is reassuring. And basically, the world now comes down to U.S. standards and European standards in a lot of respects. Is that, am I missing something here, Bill?
Well, I think, and Chinese standards,
Yeah.
sooner rather than later, I suspect.
Yes.
But one of the policy issues that has come up is if the Europeans and the Americans can agree on an approach, what you then have is collectively the largest middle-class consumer developed world market going, all moving in the same direction and all focused on the same thing. That's a formidable, not a barrier, but it really is going to force everybody else to build to those standards, which is to the benefit of our mutual manufacturers. If you end up with other countries, China or maybe eventually India or somebody else pursuing their own regulatory approach, then you're going to fragment the industry, as so many others are fragmented now, and then you have trade barriers and all those problems. Yeah. To the extent you can anticipate that, which is a lot easier with a future technology or a new technology, because you don't have any rice bowls already existing, it works much better. But for the reasons you said, that could be difficult. There's still I mean, this came up in over and over and over again in TTIP, where both sides, everything will be fine.
Be reasonable, yeah.
And that's not a recipe for ultimate success. We've got maybe a minute. I had one more question, but we've got one here, so we'll do that. And then we've got maybe last two, and then we'll.
Just to complete the standards and trade row. I'm Mary Saunders with the American National Standards Institute.
Thank you.
And coming off a long career with Commerce Department, including NIST. So just to build on Jeff's comments and also John's comments, in terms of trade barriers, it will not be solely about the standards themselves, even if we agree on harmonized standards. A standard is only useful if you can assess conformity or test to it or certify to it. So I actually think probably some of the barriers that may arise in foreign markets might be with respect to requiring local testing or local certification, local sourcing of the powders. And an interesting point I wasn't aware of that I learned about last week when I was at another workshop on 3D manufacturing is depending on what it is you're printing, it and the machine might actually be subject to U.S. export controls. So that's another, depending on the level of sophistication and what type of parts you're printing and the intellectual property involved in the software. There's also that to be considered. It isn't an issue as of yet, and I know Commerce hasn't really addressed it as part of the Commerce Control List, but it's something actually that I think some companies are certainly looking out for.
Very interesting point, thank you. And certainly, the more your substrate, the material used for printing is an organic, I can see that being carefully regulated on a local level. So,
let's close where we began.
Yes,
One more question.
TJ May again.
Yes.
From a national security perspective, you mentioned in the paper the U.S. leads in application of additive manufacturing, but not necessarily in producing the machines, for example. Again, with national security in perspective, how important is it that the U.S. contribute national resources towards domestic ability to produce software, machines themselves, expanding the menu of materials, or innovating techniques to apply all of that, or can we get by on kind of the current paradigm?
It's a great question, and my own thought is, given the interest, particularly in Defense Department procurement, one of the things the U.S. government can really supply is demand for the products, demands for the items, and the underlying industry will respond in a way that will enhance their productivity and enhance invention within the supply chain simply by procuring more components that are made this way. So I think that'd be the place I'd start. This technology is not at a point where it's a little beyond the point you call it a DARPA project, because it does exist. It's operating. It's around us. But certainly to the extent that the U.S. government, but specifically DoD and its sustainment programs, are the major purchaser here. I think what you can do is stimulate a lot of production ideas and new technologies coming to the market simply because the demand exists. So that's a place I'd start.
So it's here, it's growing, but it does not, in the next 2 years, mean the end of the assembly line.
That is correct.
All right. Thank you very much. Thank you, Scott. Thank you to all of you for coming. I hope you got a copy of the report.
Thanks for coming.